Previously on Overtime Games. This idiot yapped for 10 minutes. This time on Overtime Games, you're watching it. Something's missing from my tank. Yeah, I don't like that orange too much. What I have to do is somehow connect these two parts together. And I think I know just how to do that. Oh, there we go. Back at my desk, ensuring my designated digital indenture design delegation. I made this plate. It's gonna go on the bottom of the tank and act as a platform for all the electronics. It's also going to be made of one of the elements on my favorite row of the periodic table. That's right, magnesium. Phosphorus. Aluminum! Aluminium! Why make it out of metal, you might be asking. Did I ask? Metal is just pretty cool. Literally. I'll get back to that. 3D printing kind of makes me feel like Tony Stark. Jarvis, build this thing I made in Blender.
So that looks like
CNC machining is more like diffusing a bomb. Any mistake here is permanent, it takes forever, and I have to babysit it lest the machine thinks a hole should go right there.
It's still so cool though.
Stop. Just, nope. Okay, it's just tapping. We don't need the music anymore. It's just tapping holes. So, how's life? Oh, thank God he sped it up. I thought I was gonna have to put some clips of Family Guy on the screen. Pretty satisfying, though. Hang on, let me welcome back the 05 Zoomers. Wow, you couldn't sit through the montage, huh? As part of your rehab, pause and wait for 30 seconds. After getting metal fever for a couple of hours, I made one of my favorite 3D objects I've ever produced. Sick. Alright, let's attach the plate. I might need some more metal. I had this idea of bending some L channel into a rectangle and drilling holes in it to mount the plate on the bottom. Only problem is, I can't CNC this stuff, so I have to do it manually. So I printed out these patterns, and after enjoying some of the glue for myself, I attached them to the L channel. Then I began my caveman era. All this metalworking also makes me feel like Tony Stark, but all done. It even comes with free drainage holes. I love metal! Hey, check that out. It can roll as one piece now. Let me install some electronics to test it out. I also bought these extreme lithium batteries. I hate this thing so much. Which are running the motors at 200% their rated voltage, which works out to 400% of the rated power. I'm sure it's fine. Lipos tend to be pretty volatile, so I don't like working with them. Oh shit. Volatile. What the f? Here's the circuit I was trying to build. And there's a couple reasons this is a bad idea. First of all, there's no power switch. Second of all, if that buck fails for any reason, the Arduino will die, and so will anything connected to it. This is foreshadowing. So obviously this isn't the final product, this is just for testing. And no, I'm not going to use an Arduino in the final version, that's some kid shit. So now I gotta find a way to control this thing. What I need a control system to do is basically be able to tell the tank to move forward, backward, left, and right. I don't want to touch RF right now with a 10-foot pole, so instead I'll use a 10-foot wire. So basically I need a joystick on a wire. This was the peak of technology. If I want to use this nunchuck, I have to figure out which wire does what on this connector that I installed 5 years ago. I have no idea how I'm going to find that out with this thing though. Oh. Well, that's easy. The wires look different because the nunchuck was fried.
Test drive number 1.
Okay, we're live. That's so cool. So there's a couple problems. One, now that the body is mostly metal, it got pretty heavy. Like my suspension is like a damn That's not an edit, I hit my desk so hard that it cut the clip off. My suspension is like a damn scion. As you can see, it just exists completely bottomed out all of the time. So I had to upgrade the springs. Also, the track gets a little loose, so I added a tensioning system. Remember that grinding noise? That's coming from the notch in the plastic gear getting completely stripped away by the motor's torque. So to solve that, I have to take another departure from plastic. Driving it again, it feels a bit better, but this wired control setup means I have to chase after it like a dog. I think it's time to design some definitely professional electronics so that I can wirelessly control my dog. Time to use another CAD software. I should probably explain what all this is. This is an overview of the PCB. Let's start with the battery circuit. These 4 BTNs might be familiar. I talked about them in the last video, but these are what are actually controlling the motors. We send them a signal from the microcontroller and they turn on and off to spin the motors in either direction. There are 2 sets of 2 so that they control 2 motors. The high current sources and sinks, aka the motor and batteries, plug into the yellow connectors. These 2 capacitors are here to smooth back EMF, so that a current spike doesn't break the motor or the drivers. This MOSFET is here to act as a power switch. It's surprisingly difficult to find power switches that can handle up to 60 amps DC. So instead of going with a mechanical switch, we decided to use a solid state switch, solid state being a transistor. Also, to accommodate the high current, the traces here are very thick, and the copper is a 2-ounce pour. Let's move on to the low voltage area. We have to somehow turn the 24 to 26 volts DC produced by a 6S lithium battery into 3 volts for the microcontrollers and all of the peripherals. We do this with a switching buck regulator. There's another switching buck regulator that turns it into 12 volts. This 12 volts will control a whole bunch of LEDs. These LEDs are also solid state switched by these MOSFETs, which are controlled by the microcontroller as well. For the microcontroller, we picked an STM32. This is a particularly high-powered STM because it has onboard JPEG decoding and encoding, as well as a DCMI interface. We need the DCMI interface because it connects to a camera, which will record images from the tank and transmit them back to the controller. Digital video is a very high bandwidth application, so we had to be very careful about which wireless chip to choose. Here we went with an FGH100M. This is a fairly new Wi-Fi chip that uses the 802.11AH Wi-Fi Halo standard, which is a longer range but still high bandwidth Wi-Fi standard. This is dissimilar to XBee as we need the very high bandwidth to accommodate digital video. The antenna is a standard board edge 50 ohm impedance antenna. There's a few other components here, like an to measure currents that I haven't mentioned. The controller has a very similar setup with the same microcontroller and Wi-Fi chip, although that one operates on a 1S LiPo and has a built-in charging circuit so that we can use it in the field. Oh, look what arrived in the mail. Spilled some sand to my plate here. Oh wait, those are parts. I've also been working on the controller case. This uses a compliant mechanism for the triggers. My phone is full of videos of me filing and sawing and electronics that have their pins bridged together. And I wouldn't have it any other way. Okay. This project still has a long way to go, and I'm intent on seeing it through to the end. I'm still a pretty small channel, so if you enjoyed, consider subscribing. I solemnly swear to deliver you good content. In any case, I hope you enjoyed, and I'll see you in the next one.